Objective 10. Our final objective on practice test B is a distributive practice objective going way back to the beginning of the school year, thinking about periodic table skills. We're being asked to look up some information about the atoms in terms of atomic number, mass number, protons, neutrons, and electrons. I'd like to just write some handy notes underneath this table before I go ahead and start giving answers. For instance, atomic number is always the whole number on the periodic table that proceeds left to right, always increasing by one integer. On our periodic table, it's the blue in the top right corner. So the atomic number is always a whole number, and what that's defining for us is the identity of the atom by proton number. So by very definition, since hydrogen is element 1, 1 proton, helium is number 2, 2 protons, and so forth. So that integer as we proceed from left to right identifies the atom based on the number of protons. But since atoms are neutral, we also remember that protons and electrons will always be the same value. Proton and electrons create a neutral atom. So when you're finding the identity by atomic number, it's actually giving you two of the columns, proton and electron. Keep in mind, atomic number, the proton, and the electron will be the same number. The next column talks about mass number. And remember, the mass number may or may not match what you find on the periodic table. The mass number is found by adding the protons and neutrons together. It will also always be a whole number. What we find on the periodic table are the averages of all of the isotopes, and that's why we see the decimal points. On the periodic table, when we see the mass number, it's actually called an atomic mass, the average of all of the isotopes. So when you're filling out mass number, notice that it will always be a whole number, and it's found by adding protons and neutrons together. And it may or may not match what you find on the table. Don't be thinking that you're making a mistake if it's not matching. So for instance, sodium has a symbol, number 11. So Na is number 11. That tells me it's 11 protons and 11 electrons. 11 protons, 11 electrons. To find the neutrons, I take 23 minus 11 and come out with 12. The element called silicon has a symbol Si. Silicon is number 14, so I now know it's 14 protons and electrons. And 14 plus 17 is 31 for the mass number. So again, 14 plus 17 found the mass number. Bromine has a symbol Br. Bromine has an atomic number of 35. If its mass number is 79, already provided, we can fill in protons and electrons directly from the identity, atomic number 35, but remember 79 minus 35 is an even 44 number of neutrons. So mass numbers will be whole numbers, not the averages that we see on the periodic table. So one of the first skills we learned in chemistry, periodic table skills. Part 2 of our distributive practice takes us back to stoichiometry. We're looking at part 2, stoichiometry and percent yield. If potassium metal is placed in water, they'll react violently. Write the balanced equation for the single replacement pattern. Just as we practiced this chapter, thinking about water as HOH for the double replacement, I like to think of water as HOH in the single replacement as well. It helps me see in a single displacement the ions in the water, HOH, and potassium then displaces the hydrogen from the water. The first product is H2, and the second product is an Arrhenius base, KOH. We practiced several of those in our note pack when we defined the Arrhenius base. So the reason this is written in is to kind of integrate that note pack lesson for the Arrhenius base, a violent reaction when potassium is placed into water. To balance, we end up doubling the potassium, the water, and the base, potassium hydroxide. Letter B says, if our reaction proceeds with an 84.7% yield, how many grams of our base, potassium hydroxide, are formed when 253 grams of potassium metal reacts with excess water? It's a mass problem where we'll end up taking 84.7% of our answer. So the 3 steps to stoichiometry is where we begin, starting with the given 253 grams of potassium. We'll get our 3 steps ready for a mass problem, knowing the heart of our problem is the want over given ratio. Also remembering that we have an 84.7% yield. I'll just put that right there, so remember to do that. We're going to take 84.7% of our answer, and now I can see my target. We want to know grams of KOH, the Arrhenius base. Given a mass, we'll calculate a mass. So, first step, we'll need a molar mass of potassium, we'll call 39 grams in every 1 mole. We want the base, its coefficient is a 2, starting from the potassium, whose coefficient is also a 2. And in the last step, we'll need the molar mass of our target, potassium hydroxide. So I'll add that, 39 on the potassium and 17 for the OH, and I get 56 grams of KOH in every 1 mole. Let's hit together and see if we get our common answer. We have 253 grams of potassium as the given amount. Divide by 39 the molar mass. Our ratio of 2/2 drops out, and we'll multiply by 56 the molar mass of our base, times the percent, the efficiency of the equation, 0.847. There, I got it. And I find 307.7 grams of KOH. Waiting for a nod. Perfect, thank you. One more in this part. How many liters of hydrogen are produced? And here's the nice part, my friends. Assuming STP, so there's no Puvnerts involved. It's nothing to do with gas laws. It's straightforward stoichiometry. Assuming STP says we can use 22.4 liters in that last step. Alrighty. So we'll begin with the same starting point, 253 grams of potassium. We just have a new target. It's the hydrogen gas. We still have an 84.7% efficiency. We're just targeting now the liters of H2 in our stoichiometry journey. So given a mass, we'll calculate a volume, a mass-volume problem, where the heart of our problem is the want over given ratio. 253 grams of potassium, same first step. We'll just put that under its molar mass. The target of hydrogen has a coefficient of 1, set under the coefficient for the potassium, so we get a 1/2 stoichiometric ratio. And because we're at STP, we can put in directly that 22.4 liters of hydrogen for every 1 mole of hydrogen can find our volume. We'll hit, starting with the mass, 253, divided by potassium's molar mass. This time we have to divide by 1/2, multiply by the molar volume, 22.4, and the 84.7% efficient reaction. How about 61.53? Excellent. All right. We'll keep going. We'll look at part 3. This takes us back to when we were learning about empirical and molecular formulas. A molecular formula is some ratio that when chlorine and oxygen combine gets me a target weight of 182.9 grams. When we're finished writing our formula between chlorine and oxygen, we better make sure its formula weight is targeting about 182.9 grams. If our percent composition is sharing that we have 38.8% of its mass coming from chlorine and 61.2% of its mass coming from oxygen. We'll work to convert both of these into mole units and see what kind of ratio we have going on. So 35.5 is the molar mass of chlorine, 16 being the molar mass of oxygen, and let's find the number of moles of each of the ingredients. So we'll hit our 38.8 divided by 35.5 gets us 1.09 moles of chlorine. And we have 61.2 divided by 16, 3.825 moles of oxygen. Our strategy says we need to turn these decimals into whole numbers. And what we've learned, the easiest technique, find the smallest one and turn it into a 1. Divide all of them through by the smallest number. The moles of oxygen, 3.825, divided by the lowest number, 1.09, gives us a number of 3.5. Right now, we have a 1 to 3.5 ratio. We're not allowed to just round that 0.5 away, but instead we keep the proportion the same, and we do that by doubling both. When we double, we come out with a 2 to 7 ratio. So here's what we have so far. Chlorine with its subscript of 2, oxygen with its subscript of 7. How close are we to the target weight of 182.9? So let me just write that as its target weight, and it's a way to double check if our formula is actually correct. So let's add that. Chlorine is 35.5, but there's 2 of them, so times 2, plus 16 times 7 for the oxygen, and we get 183 grams. We have indeed hit that target weight or close to it. So now that's just a way to confirm we're correct. Cl2O7, the empirical and molecular formula. The last part of our distributive practice reviews some gas laws. This is an experiment we actually ran called the Dumas bulb technique for determining molar mass of a volatile liquid. We vaporize the sample in a boiling water bath and then plunge it into cold water and see how much of that liquid recondenses. Here's what we've done by collecting the following data.